So now we look at other forms of the Green's theorem. Well, so the first version of Green's theorem was used to find the circulation along Z by the force field, by the vector field in this case. Now, and in this situation, we were using the tangential at every single point. So back then it was at every point circulation, all these infinitely many mini circulations. But now we're going to look at flux essentially. And flux is related to the normal component. Now it's how much of the vector field is going outside of that region or against the region, depending on the sign. Well, that's the thing, of course. And well, so in this case, instead of calculating the line integral f dr, we're going to go f dotted with n ds. And well, here is the cyclic integral that we will evaluate. Notice the change in the signs right here. And in this case, well, formalizing this form. In this case, we're not going to use the curl of the vector field, which we will talk about the curl in the next section. This time we're going to talk about the divergence of the two-dimensional divergence of a vector field. Well, actually, of a function rather. And well, it's going to be essentially the same, except that these partial derivatives right here now, they both have positive signs. And in this case, we take the partial of f with respect x and the partial of g with respect, well, that's the divergence for now. Let's just use it like as is. Actually, we're going to make more sense of it in the next section. And well, so because this form uses the divergence, which is essentially how much is flowing out or flowing in, well, depending on whether we have a source of a sink, actually. We also call this the normal or divergence form. The previous form was the tangential or curl form. So there's two forms of Green's theorem in this case. And well, let's do one example and wrap up the section. So in this case, we're given another vector field, x minus y comma x, over the region bounded by the unit circle. So in this case, they're asking us to find both. Number one, the circulation and the flow. So here is as a picture. Here's what they're essentially asking us to find. So let me draw a Cartesian plane and sketch the region. In this case is the unit circle. So that's the unit circle. So we're going to use the first form of Green's theorem to find the circulation, that is along the tangentials. And this new version, which involves the divergence, we're going to go about the normal vectors. In this case, how much is going outward or potentially inwards, depending on the sign. If it's positive, well, we're dealing with a source. And if it's negative, in this case, these arrows would be pointing towards some sink in this case. Well, this makes more sense in physics when you're dealing with fluid mechanics. I don't know if any of the physics courses here deal with that. I think it's the physics 3, the one that you get to see those fluid mechanics. The second one, I think it's electromagnetics, right? I think so it is.
You do it in 272.
272, a little bit of hydraulics, and all right. So yeah, you'll apply a lot of this in physics. Well, let's look at one example. So number one, circulation. And for circulation, we use the first version we learned. That's f dr over c. That's the double integral of r. And in this case is the partial of g with respect x minus the partial of f with respect to y dA. So in this case, well, so what do we have? We have f which is x minus y, and g which is simply x. So the partial of f with respect to y equals to -1, and the partial of g with respect x equals to 1. So let's evaluate the integral via Green's theorem, the curl or the tangential form. So this will be the double integral over r of 1 minus -1 dA. Do we even need to evaluate a double integral, set up the double integral? Not really, because we can just take out that 2 and leave it in terms of area. I mean, of course, you might want to even set up the integral in polar form, but why? I mean, it's the area of the circle in this case. What's the area of the unit circle? Isn't that 2 pi times 1 squared? And that's simply 2 pi. So that's how much is circulating along the circle. Now, how much is going out or maybe coming in? Well, depending on the sign, we'll find out. But in this case, we will know that when finding number 2 by means of finding flux in this case. So flux. And we're going to look at flux integrals in more detail when we get into surface integrals. And I'm not sure if we were going to get into that today. We'll see. So this is going to be the integral of f, but in this case over the normal components. That's the double integral, and that's the other form of Green's theorem. Partial of f with respect x plus partial of g with respect to y. And in this case, we're computing the divergence as opposed to computing the curl like we did in part 1. Well, so, and how about we take the partials again, because in this case, okay, so now we need to find the partial of f with respect x. So the partial of f with respect x is 1, and the partial of g with respect y, that equals to 0. So that's going to be over r, the double integral over r of 1 plus 0 dA, and that's simply the double integral dA over r. And well, it's the unit circle. What's the area of the unit circle? 2 pi. Hold on, why did I get a pi actually? Yeah, it's pi, right? So pi times 1. And well, in this case, it's positive. In this case, we have a source. So that means it's going at a rate of, it's flowing out of the region at a rate of pi.